So I'm going to talk about improved generic attacks against HMAC and HAIFA. And first, let me begin with a bit of introduction. So by now, I guess you all know what HMAC is. You have had 2 talks about it already. But so it's a very common MAC algorithm, and it's based on a hash function. So if you want to use it, you actually have to pick a hash function. So maybe you can pick MD4, MD5, SHA-1, SHA-2, but maybe if you're Russian, you're going to pick some Russian standards rather than an American one. And in particular, there's a Ghost standard for hash function, which was designed in 1994. And if you look at HMAC based on this Ghost hash function, it looks like this, basically. And you have an L-bit state. You iterate this, and well, in the end, you expect that key recovery attack should cost about 2 to the L. That's what you expect from HMAC usually. Now, in this specific case, if you put HMAC with Ghost, it turns out that there is an attack which is much more efficient than this, with complexity only 3L/4. And that's something that was showed at last Asia Crypt. And that's a really very surprising and very strong result. So why do we have this? The main reason is because of this internal checksum. Here in Ghost, you have this extra line where you do a checksum of all the message blocks. And the way the attack works is that first you have to do a state recovery attack. So you have to recover the state after processing some known message. And that's actually one of the main results also in this Asia Crypt paper. And when you do this, after that, you can also change the message. And what happens is that you do a kind of related key attacks, because this checksum contains the key and also contains the message block. So if you put differences in the message, you do a kind of related key attack on this finalization here, and in the end, you can recover the key. So well, the starting point from this work was that there's actually a more recent Ghost hash function than the one I described here. There's one that was published very recently, and it's called Stribog, and it looks a little bit like the old one. So maybe there's hope that we can do a similar attack. In particular, it also has a checksum like this, so we can do the same trick of turning a state recovery attack into a key recovery attack. The problem is that to do the state recovery attack, it seems a lot harder because it's based on the HAIFA iteration, and this means that the compression functions at each step are different. Instead of having always a function h, here you have a different one for each step. And because of this, the previous attacks cannot be applied as is. And so that's the main goal of this work. Try to see if we can do a state recovery attack on this construction, and then this will hopefully give us a key recovery attack on HMAC Ghost. So more generally, if you look at the state of HMAC, we know that there's a security proof up to 2VL/2. We know that there's a matching attack for existential forgery, and also for various stronger attacks. We've had a lot of very recent results, in particular a state recovery attack with 2VL/2, but that's only for Merkle-Damgard iteration, not for HAIFA. And also universal forgery attack that you just saw in the previous talk with complexity 3L/4. However, there are some limitations in these works. So first, they don't apply as is to the HAIFA iteration, so they will not work on Stribog, so that's why we started working on this. And the second problem is that they require some very long queries of length about 2VL/2. So in practice, that doesn't look very practical to have those really, really extremely long messages. And actually, even if you look at the specifications of many hash functions, like SHA-1 or SHA-2, you can see that the maximum message length that they accept is limited. There's a fixed limit in the standard. And in particular, for SHA-1 and SHA-256, it's only 2^55 blocks, and that's a lot smaller than 2^2. So the previous attacks cannot really be applied. So that's also a second area where we'll try to improve the previous work. So in this talk, I'll just describe the attacks on HMAC HAIFA, and I'll briefly mention the results about having attacks with short messages. So what happens when you use a hash function-based MAC with a HAIFA hash function? So you'll have some kind of internal state. We denote the state size as L, so we have an L-bit state. So initially, you have some value that depends on the key, and then you iterate your message block. So since we consider a HAIFA-based hash function, we have a different compression function at each step. But the compression function does not use a key. That's a very important point. And then at the end, you have a finalization function that does use the key. So how can we do a state recovery attack on this kind of construction? Because that's going to be our main goal here. So the basic idea is that you're going to do 2 main steps. So some computation that you're going to do online using the oracle, and some computations offline, because you can compute the compression function yourself, because it's completely public and doesn't use a key. So you're going to send a bunch of messages to the oracle, and this will implicitly define some states that are evaluated by the oracle. And then you do some computation offline by evaluating the compression function yourself. And then you hope that if you have enough points on both sides, there should be a match between them. You do a kind of birthday match. And you hope to detect one point that is in both sides. And if you can detect this, then, well, in the offline evaluations, you know exactly the values. And then in the online state, you know the messages. So you're going to recover the state after some fixed message. So there are two important problems when we want to do this. The first one is that there's no easy way to compare online and offline states. So we'll have to find out how to do that. And the second is we have to be careful about how many comparisons we're going to do. So I start with this, how many comparisons we need to do. And in order to reduce this number of comparisons, we're going to use some special states that we can force the oracle to go through a small set of states. And this is actually something that was used in the previous attacks, in particular using the cyclostructure of a random graph, like you've seen in the previous talk. Because if you have a fixed compression function, then you can see it as a random graph. And if you iterate this fixed compression function, at some point you reach a cycle, and it turns out that most of the time you use the same entry point. So that's a very specific point that you can reach very easily, and you can force the oracle to go through this point. And then if you use this point as special state, then you have just a set of size 1, so it's much easier to do the matching. Unfortunately, for HAIFA, the previous technique cannot really be used because we have different compression function every time. So we need to do something different for our special states. And what we do is that we just look at the entropy loss when iterating random functions. And we know that if you evaluate a random function, the output state, of course, is smaller than the input because you have collisions. And more generally, if you iterate a sequence of random functions, then the output states get smaller and smaller. And in fact, the loss that you have is that if you have a sequence of 2 to the s fixed function, then the output size is about 2 to the l minus s. So you have a linear loss of entropy. And that's also something that has been studied in previous work, for instance, at last FSC. So with this in mind, we can try to build an attack on HMAC HAIFA. So we're going to use some fixed sequence of random function. And in order to do that, we first fix a long message C, and we're going to send this message to the oracle. And when we fix the message, we fix the sequence of functions, and then we'll have those lines of iterations here. So first, we're going to send messages to the oracle, and we start with one block that we use random values or a counter, so that we just send the initial state to a bunch of different values, and then we go through this fixed chain. And the idea is that those states at the end, the blue states, they live in some small set because of this entropy loss. Then we do the same offline. We start from random points. We evaluate those public functions. And we have another set of values in this small set. And then we try to match them. So according to the analysis here, we know that we need to have s plus t plus u equals l, where u is the number of online chains, t the number of offline chains, and s is just the length of the chains. So that's the basic framework. Now we need to be able to compare those sets of points. So we have those online states and those online states offline, and we want to test whether they're equal. And the way we do this is using filters. And the filter will be basically some way to compare those states. And what we use is collisions, because we know that collisions will be preserved by the finalization function. So the first thing that we do, so we have some message m, and we have some state x that we know, and we want to test whether the state after m is the same as this x that we know offline, or whether they're different. So the first thing we do is we start with this state that we know. We evaluate the compression function with some random blocks, and we wait until we have a collision. We denote this as pp prime. And then we just take this message m, and we evaluate mp and mp prime. We send them to the oracle, and if they have the same MAC, then it means that most likely the state was x, and then we have the collision because this state is x. So now we can actually compare those online and offline states. So if we put everything together, this is what it's going to look like. So we first evaluate chains offline. So we start from random point, evaluate chains. When we have the end point, we build a collision filter. That's the first phase. Then we move online. So we build those messages with random blocks and this fixed message. And then for each online and online point, we use the filters to compare whether those points are equal or not. So that seems easy enough. There's just one simple problem, is that if we look at the complexity, we have to do 2 to the t plus u comparisons, because that's the size of both sets. But each comparison is very expensive, because we have to send a pair of messages to the oracle, and the message of length 2 to the s. So the total complexity is 2 to the s plus t plus u, and unfortunately, that's exactly equal to 2 to the l, so this is not better than exhaustive search. So we need some new tricks to improve this, and in particular, we need a way to do the testing more efficiently, because that's the bottleneck here. And one very simple trick that we found out is that we can actually reverse those operations. So in the previous case, we build the filter offline and we use it online. And now we do just the opposite. We're going to build the filter online and use it offline. So we first send queries with our fixed message m and some random blocks, and we wait until we have a collision. And then this collision pp prime can be used as a special property of a point after m. And then when we have an offline candidate, we just evaluate the compression function from there. So when we do it this way, the important difference is that building the filter is a lot more expensive, because we have to use long messages and send them to the oracle. But using the filter is now very cheap, because we have very short messages. And when we put this in the previous attack, so now the filters are on this side, on the online side. When we do it like this, then testing all the values only costs 2 to the t plus u, so that's less than 2 to the l. So there's hope that this will work. So when you look at all those complexity, you have to check the optimal parameters to optimize this, and it turns out that you can choose them so that the complexity is 2 to the 5l over 6. So we do have an attack on HAIFA, state recovery attack, so that's a really nice result. We can actually apply the previous, well, similar attacks as the previous one. They can also work if you use HAIFA. So complexity is a bit high, however, so we try to use a few more tricks to improve this. And in particular, in this attack, one very expensive step is building all the filters, building all those collisions here, because we have 2 to the u of them, so that's a really large number of them, and that's a very expensive step. So what we try to do is to amortize this, because we build many filters simultaneously. And there's actually a relatively simple way to optimize this. It will be using a diamond structure. So a diamond structure is a structure where you start from a number of points, and you want to send them all to a common final value using different messages. And now what we do with this is that we build this diamond structure, and then we build a collision filter at the end of it. And now this gives us filters for all the initial points, because you just have to select the correct message to follow the diamond and then use the pair at the end. And what we gain by doing this is that the cost now becomes a square root of n, where n is the number of points, times the complexity of one filter. So we really gain by building them simultaneously using this diamond structure. So again, you can plug this into the previous attack. So now we build this diamond thing. Again, we can look at the complexity of each step. Now we have significantly improved this step here, because now it's s plus u over 2 plus l over 2. And previously, it was s plus u plus l over 2. So we have removed half of u. And again, we can optimize the parameters, and it turns out that we can go down to 4l over 5, rather than 5l over 6. So this is one more improvement. So basically, this is our attack on HAIFA. And now I'm going to talk very shortly about attacks with short messages. So the attack I described is just this dashed line here. So it can go down to 4l over 5. And using a few extra tricks, if you look at the paper, we have a stronger attack where we reach the same complexity, but using shorter messages. So it's not more efficient, but it uses shorter queries. So that's still a nice improvement. And then we also looked at all the tricks we used to apply this attack on HAIFA, and we used them on Merkle downguard. And then we can also improve all the previous attacks. So the previous results are this green line here, and our new results are the red line, and we can see that in most cases we have a significant improvement for a given maximum message length. We can reduce the complexity. So we also looked at universal forgery attacks, like described in the previous talk. And if we look at the attacks published before, we can see that all of them require long queries of length 2 to the l over 2. So they cannot really be applied to concrete hash function like SHA-1 or SHA-2, because those messages are just too long and they're rejected by those hash functions. So in the paper, we give attacks where the query length is smaller. So this can actually be used in practice for those hash functions, but the complexity cannot go down as low as on those works. So we don't go to such a low complexity, but we can use shorter messages. So there's again a kind of trade-off. So to conclude, we have three kinds of results. The first one is we improve the state recovery attacks on HMAC with Merkle downgrade. And if you look at those complexity, those are the blue results. So these are the complexity of previous work, and we can improve in most cases. The second class of result is that we improve the universal forgery so that it works with short queries. And then this means that we can actually apply it to the SHA function or Haval or Whirlpool, while the previous work cannot be applied because of this limitation of the message length. And finally, we have results on HAIFA, and we have a state recovery attack. So we have the first results that can be used on Blake, Scale, or Stribog, and many recent hash functions also use HAIFA, so it's really nice to have results on this construction. And finally, we have this very interesting result here, that if you use Stribog with HMAC, then we can do a key recovery attack. Because we now have a state recovery attack on HAIFA, and we can use the same tricks as the Azure-Code paper using the checksum to turn it into a key recovery attack. So this means that actually if you do HMAC Stribog, it's going to be weaker than if you do HMAC SHA-512. So the attack is not practical, but it still means that there's something kind of wrong with these constructions. So this will conclude my talk, and thanks for listening.